Generative AI is now built into the everyday workflow of higher education. Students use it for drafting essays, generating code, and summarizing dense readings. These tools offer real benefits. They can lower language barriers, make materials more accessible, and reduce the anxiety of a blank page by instantly accelerating the first draft. However, the extreme fluency of these tools allows a student to reach a finished product before they have built the knowledge needed to evaluate it. This leads to premature task completion. Traditionally, a student receives a task prompt, pushes through a student draft, and creates a polished output. Generative AI compresses this process, reaching the finished product instantly. But that bypassed middle step is where effortful work happens, where learners build mental models and surface misconceptions. When AI removes that struggle, the result is an illusion of explanation. The output looks coherent, masking the fact that the student's underlying understanding remains shallow. Higher education cannot respond with blanket bans because the technology is already ubiquitous, but uncritical adoption is equally dangerous. Instead, educators must treat academic difficulty as a deliberate instructional design variable. This requires a specific pedagogical approach, the principle of scaffolded friction. In this framework, friction is the productive resistance that forces a learner to generate, test, and revise their own ideas. It prevents them from simply accepting plausible AI answers at face value. Scaffolding is the intentional structuring of that resistance. The difficulty is bounded and staged, ensuring students can persist without becoming overwhelmed. To make this work, instructors must first establish psychological safety. If early imperfect attempts are penalized, students will use AI to hide their uncertainty. A safe environment rewards the messy process of revision. The goal is to systematically sequence the learning process. By doing so, generative AI functions as a temporary scaffold to build understanding rather than a permanent substitute for human thought. Productive struggle is a targeted design choice. It requires a clear distinction between effort that builds a mental model and effort that merely adds a layer of administrative difficulty. This 2x2 chart balances cognitive support on the vertical axis against cognitive friction on the horizontal. Unproductive struggle, like busy work or vague instructions, consumes effort without strengthening learning. Conversely, productive struggle means testing constraints and repairing errors, generating the mental effort needed to create knowledge. Left unchecked, generative AI naturally pulls assignments toward the low-friction side of the chart, shifting students out of the productive zone before they are ready. To keep students in that productive quadrant, instructors must intentionally protect specific cognitive moves. Actions like problem framing, evidence verification, and justifying a claim must be insulated from immediate AI automation. This chronological workflow puts scaffolded friction into practice across 4 sequential modes. First is struggle, an attempt-first mode where AI access is completely blocked, forcing the learner to face the blank page. The output of this initial struggle must be a tangible artifact, like a crude problem outline, a concept map, or a list of assumptions. Once that initial attempt reveals specific gaps in understanding, the student moves to support. Here, carefully bounded AI assistance is unlocked. This assistance acts as a hint ladder. The AI is constrained to act only as a critic to flag missing evidence or as a generator of practice variants. It is never allowed to provide a full solution or write a complete draft. Next is reflection. The learner must now evaluate exactly what changed between their initial attempt and the AI-supported revision. This step requires artifacts like an error log or a verification checklist. Documenting how they verified the AI's output prevents the illusion of explanation and anchors the new concepts in their memory. Finally, the student reaches transfer. This tests the durability of their learning through a short in-class task in a novel context entirely without AI to check their independent performance. This sequenced loop guarantees a specific order of operations. AI only accelerates the workflow after the student does the heavy lifting of building mental models. Because generative AI shifts the cost of cognitive tasks differently across subjects, this framework has to be adapted to fit specific academic disciplines. Look at this split-screen comparison, showing how AI disrupts essay writing on the left versus quantitative problem-solving on the right. In writing courses, the tool can generate fluent prose instantly. If you only assess the final text, students bypass the thinking entirely. Therefore, the protected cognitive friction must be moved completely upstream. Instructors can use an argumentation portfolio. Students must submit a concept map, tag their evidence, and annotate their sources long before they are permitted to use AI to suggest stylistic edits on their draft. Now look at STEM courses. AI can propose mathematical solutions, but it frequently hallucinates steps or relies on completely invalid assumptions. In these disciplines, the protected friction must be placed squarely on problem representation and rigorous validity checks. This requires an attempt, check, consult protocol. Students submit a first-pass attempt and run dimensional checks on their own before they are allowed to consult the AI for alternative solution paths. Whether teaching argumentation or data science, the universal imperative is the same. We must separate the mechanical production of options from the human judgment required. The move towards scaffolded friction reflects a shift in how we view assessment. In an AI-rich environment, the traditional take-home essay and independent problem set lose their ability to measure individual competence. Relying on AI detection software is a failing strategy. It creates a technical arms race where the plausibility of generated text consistently outpaces the ability of a statistical classifier to flag it. The alternative is proactive. We must design academic integrity directly into the grading workflow rather than trying to police it after the fact. This means adopting standard disclosure norms. Students should transparently report their AI prompts and document the specific routines they use to verify the machine's output. Consequently, the grading rubric itself has to change. Instructors should stop evaluating only the final polish of a document and instead measure the quality of the initial attempt, verification rigor, and the revision rationale. When the assessment actually rewards transparent process and rigorous verification, students are practically incentivized to engage in productive struggle. Generative AI is undeniably powerful. It excels at producing drafts, rapidly brainstorming options, and accelerating complex technical workflows. But there is a hard limit to its capability. These cognitive responsibilities must remain the protected domain of the student. Upholding this standard is a broader institutional responsibility. Redesigning pedagogy requires supporting faculty workloads and ensuring equitable access to approved AI tools for all learners. Struggle in learning is not a defect to be engineered away by technology. It is a vital, irreplaceable resource. By deliberately designing friction into our curricula, we ensure that artificial intelligence serves as a scaffold for deep learning. We protect the cognitive labor that builds the independent competence of the next generation of thinkers.